Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. So on today's episode we have Professor Michael Mahoney, who is one of the world's leading experts on machine learning, mathematics, and computer science. He's also somebody who I've got to know over the past year and has been a great help in understanding this space. He's, among other things, an Amazon scholar, so we've managed to work together a little bit. And hopefully, as you can tell from this episode, he's a really nice guy and has a great sense of humour and such an intelligent person. Where do I start to talk about what he's done? Well, he's a professor at UC Berkeley in the Department of Statistics. But he's also at Lawrence Berkeley National Lab. And as I mentioned, he's also an Amazon scholar and has a few more hats as well. He, if you look at his Google Scholar, which for a lot of academics is a way of, getting a look at what they've done, he has some pretty impressive statistics. And one that sort of comes to mind, not only does he have more than 36,000 citations, which is a lot. His H-index is 84, which is very high. But what's more impressive is, and again, this is probably going more into the details, but it makes a difference. If you go on Google Scholar and you look at the number of citations, his is exponentially growing. So not only does he have more than 30,000 citations, a H-index of 84, which is already in the very high sort of top 1% or probably even higher, it is increasing like this, which basically shows that his research is becoming ever more relevant every single year. It's not plateauing or going down. That's actually very impressive, and that shows why he is so highly regarded, because his work is really cutting edge. There are many, I think it's fair to say that because he has that mathematics background and that computer science background, he's put his hand to many different things. But one thing maybe relevant for the listeners or viewers of this podcast is a paper he did with some colleagues on characterizing possible failure modes in physics-informed neural networks. And this is, you hear many people talk about PINs, physics-informed neural networks, and so they did a great paper a couple of years ago looking at some places where it may not do so well. We talk actually about that in the podcast. We go through some of the themes I've discussed with other leading ML experts. And we talk about, for example, his opinion on, do you really need to include the physics in this AI for science regime, or is it good enough just to use data? We discuss this at length, and we also get into the topic of foundational models for science, something that he's actually really being a leading voice on. He's given numerous keynotes at important seminars and published papers in this area, so we have a good debate about that. But we actually start off the conversation talking about something he's also very well known for, which is randomized linear numerical algebra, which is quite a complex topic, to be completely honest. And I don't think we got to the bottom of it in this short talk. But it really shows that some of his work from the pure math side, or purer math side, is coming through and being relevant as we increasingly look towards lower precision methods and ways of doing mathematical tricks to try and improve the speed of many linear solvers, which are common, of course, in many, many fields of science, including CFD. We also talk about his general opinions or advice for people looking to move between academia and industry, just general career advice, something he's well placed given that he has an incredible academic record, but is also very close to industry and sort of industrial applications as well. An hour or an hour and a bit is not really enough to go through all of this, but I certainly learned a lot, and I really enjoyed talking to him, like I do every time I speak to him, and I hope you'll find the same thing. I will add some links if you're watching this on YouTube, because again, he's published so many papers and done so many great talks that I really want you, after watching this, listening to this, to go to his website and look through all of those. And obviously, if you are watching this on YouTube, you may prefer to listen to it. Some people don't realize that these podcasts are in video form on YouTube, but they're also on Spotify and Apple for audio, and vice versa. If you normally listen to this and you didn't realize there's a full video version, you can go to YouTube. So yeah, I hope you enjoy this conversation with Professor Michael Mahoney. One topic that you mentioned to me when we were chatting in the past that I was fascinated by, but if I'm being completely honest, I didn't fully understand. So it's good for my purpose and for everybody else, was around the randomized linear algebra. What exactly, for people who don't know, what is it, and why is this becoming even mentioned on a Netflix show?
This was a sign of success when it was finally mentioned on a Netflix show. The Lincoln Lawyer, a couple of years ago, someone sent it to me, and it was mentioned in one of the courtroom scenes. So randomized linear algebra, randomized numerical linear algebra is basically an area that uses randomness as an algorithmic resource to solve linear algebra problems. A lot of linear algebra problems are under the hood, whether you're doing machine learning or scientific computing. They manifest themselves in different ways. So the exact questions and numerical issues and so on are different in those areas, and that's the source of maybe tension in the area, but also synergy and part of the reason a lot of people are interested in it, because it holds the potential to solve a lot of problems people look at. But it's solving core linear algebra problems, and linear algebra problems appear at a lot of places. If you're solving partial differential equations, it's linear operators or iterated form of linear operators appear. If you're solving machine learning, you may be interested in support vector machines or ensembling methods, or these days deep neural networks. And so matrix multiplications are at the core of a lot of that stuff. So very core linear algebra problems. I think historically the way people thought about the relationship between linear algebra and randomness or noise was that there's randomness and noise in the world, meaning the data you measure, think of least squares, and it's your job to clean it up, and then you call a linear algebra problem, least squares or low rank approximation, and you get more or less a deterministic answer, and you get more or less the exact answer. I mean, and I say exact in scare quotes because there's numerical issues and you can't represent square root of 2 on a computer, but insofar as machine precision is exact, I mean, you get an exact deterministic answer. And for a lot of things that's just overkill, and so you can use randomness as an algorithmic resource, meaning inside the algorithm, to speed up computation. And this may be most notable historically, like in Monte Carlo or Markov chain Monte Carlo, where you run simulations of fluid dynamics. I mean, the Metropolis algorithm was developed in that context. But this is for core numerical linear algebra problems. And so most people, if they're running computations, sit on top of BLAS and LAPACK and related software. And if you're calling Python, you're calling something else, you're calling something that's calling something that's calling them typically. And so these are core libraries. And so the question is, can you use good theory from randomness and measure concentration and high dimensional probability to improve those algorithms or improve variance of those algorithms? The short answer is that you can.
So how does it work in practice then? So if I'm solving a PDE and I'm normally using some sort of linear algebra library, and it takes me this time or this amount of flops or this compute, how is it that the randomness reduces that?
Yeah, I mean, when you're solving a PDE, you're typically solving it for a particular application, and you're calling certain core linear algebraic primitives in one way or another. So, for example, if you're solving it with a splitting method or a predictor-corrector method, or you're solving a finite element or finite volume, or you're solving a second-order optimization as a piece of that PDE solver, these have least squares, linear solves, things like this under the hood. So typically you're improving those. You could improve the modeling setup for the PDE also, but you could try and solve improve the core primitive. So take least squares as an example, a low rank approximation. A common motif in a lot of these algorithms is you have the data and you want to solve the least squares of the low rank problem. And you could solve it exactly, machine precision or whatever. But you might want to, on the other hand, get what they call a sketch of the data, which is roughly a small number of data points. It could be a small number of actual data points, or it could be what they call a random projection. And if you're familiar with signal processing and electrical engineering and physics, think of this as like a randomized version of a Fourier transform. So it takes some signal that might be localized in space and spreads it out everywhere. But you don't need this to be a physical space. This is just a linear algebraic problem, and so you have columns and rows. So you could select the important columns or rows, or you could do this random projection, which is essentially basically a random type of rotation that spreads the information out and then sample uniformly in that rotated space. And so you take this sketch, and you could do one of a couple things with it. So some communities, the more theoretically inclined communities, want to take that sketch and solve the subproblem exactly. And there's a range of theoretical work that says the solution to the exact solution to that subproblem, computed any which way, a traditional solver or something else, is epsilon close to the exact solution to the original problem if you set things up right. Now, in a lot of cases, that is sort of coarse because it's hard to get machine precision just by drawing a sample and solving the subproblem, unless you take a huge number of samples, just because Monte Carlo methods tend to converge slowly as a function of the error parameter. So you could take that, low quality, low precision, but not trivially bad solution, and ask yourself, what is a preconditioner? And by preconditioner, I just mean a preconditioner for a PDE solver or least squares or a linear solver. And a preconditioner is basically a low quality solution that you refine. So you can actually take this preconditioner this sketch that the theoretically inclined people just say good, done, I'm epsilon good, and you can say, now I'm going to take that epsilon good, where epsilon is 0.1, and just use any of a range of traditional iterative solvers and drive that epsilon down to 10 to the minus 8 or 10 to the minus 16. And just like most preconditioners, if the cost to construct it is less than the cost to, the cost to construct it plus iterate is less than, the algorithm you're competing with, you win, and it's a good preconditioner. So there's a range of ways people solve it that way. So those are called sketch and solve and sketch and precondition, respectively. Increasingly, for machine learning applications that want medium precision, also relevant for scientific computing when you're interested in low precision data representations, going to half or quarter precision, which is increasingly seen in hardware. There's a more subtle interplay where you can get the solution and then you can iterate it and get a second sketch and toggle back and forth. And if you set the parameters differently, you can get intermediate solutions, 10 to the minus 2, 10 to the minus 4, 10 to the minus 6 quality. So there's a range of ways you can use the sketches. But roughly, the idea is you get most of the information in the sketch and solve it or do something with it.
And is there any, rough orders of magnitude of the savings that you could get? If I'm doing a Navier-Stokes solver or I'm solving some neural net using these randomized, numerical linear algebra versus a BLAS or LIMPAC, are we talking, a 10% saving? Is it an order of magnitude, or is it still under research and so it's not delivering the full yet?
Yeah, I think the question of how well you improve upon something depends strongly on what your baseline is. And if you feed this into a big PDE solver, there's a lot of moving parts and you're competing with very mature code, and it'll do a little bit better or even a lot better in a solver may or may not matter for the downstream use case that the scientist that is looking at the PDE solver is interested in. Go to the other extreme and you want to say, I want to compete with BLAS or LAPAC. These are extremely optimized pieces of code, and it's hard to beat them. So one of the big successes in the area was with Blend and Pick, and then soon after that was LSR and Blend and Pick, which said we want to ask whether these randomized sketches, not in theory, not big O notation, not whatever, can they beat LAPAC? Because this is not boutique code you have or I have or a solver that you don't share with the community so well. This is something that's been stress tested for decades. And the answer is yes. Basically on any tall, dense matrix, you can beat LAPAC with these techniques. You got to set parameters right and be a little bit careful, but the short answer is yes. How much you improve it by depends on the aspect ratio and depends on properties of the matrix, but think of it as ballpark 2 to 10. Now this was back in 2010. And so a lot's changed since then, in particular in the hardware landscape with respect to GPUs and hardware heterogeneity and the sun-sending of Moore's law and Dennard scaling and these sorts of things. And so it is the case that you could be a factor of 10 better. Similarly, in low rank type approximations, I think the way scientists versus machine learners use low rank approximations is very different. Scientists tend to say low rank means 99% of the Frobenius norm, meaning 99.9% of the Frobenius norm, or 99.99. I mean, basically the whole matrix. When machine learners say low rank, they mean the spectral norm. When machine learners say low rank, they mean 50% of the Frobenius norm. In which case, you lose a lot of information, but you might iterate and do something better. So think of sort of scaling laws in the neural scaling context with neural networks. And so the way you'd use those low-rank algorithms and feed them into other solvers would be very different. And then that would lead to very different levels of improvement. And so I think that's largely open. And then with the memory wall that you're increasingly seeing in general, but most egregiously in the machine learning applications, one of the big wins, and it's just starting to be explored for the randomized techniques, is basically improving the memory properties. And so this could be just reordering algorithms in the sense of communication, avoiding linear algebra, but it could be much broader because the randomness sort of decouples things, makes it easier to parallelize certain sorts of computations. And so you see much bigger than factors of 2 or 10 improvement there, but then again the baseline's changing year to year as people explore different representations and low precision and intermediate precision and stuff.
Interesting. So how was it mentioned in Netflix then? Going back to the full...
Well, the particular I think so. I'm not a movie star or a movie producer, but I have a sense that they want to. I mentioned this to someone, and they said, "You know what that means?" They tried to take the most exotic thing that wouldn't make sense to anyone and cited it. So the context was, I think it was early on, and the main character, who was the attorney, needed to represent someone, and the person had to get out of whatever they were charged with, which was not a relatively minor thing, but it was the 10th time they did it. And so the Lincoln lawyer said, "Why do you need to get out?" And they said, "I have a defense on Thursday. I need to get out." And he asked, "What's the topic?" And they said, "Randomization and numerical linear algebra." So that was the context of how it was mentioned there.
I wonder how they found that out. I wonder how they actually...
Yeah, I don't know. They didn't call me up, so they must have had someone in movie producer land or something that did a Google search on something exotic and came across it.
That's funny. Yeah, that's reminds me of the... did you ever like Star Trek?
Yeah, I used to see... There's a bifurcation, which maybe would get us into a separate discussion, which we need not get into, whether you like the original version or the second version. But then there was this explosion of different versions of it.
Yeah, I was more of a next generation person, but the reason I mention it is it was often whenever they wanted to explain how they were breaking the laws of physics, some stupidly complicated phrase was used, and I'm sure it exists somewhere, and it just reminds me of that, explanation of how they're exceeding the warp drive. Oh, it's because the something.
Yeah, so I think it was a little bit like that. I mean, I think it's a sign of the times that what they're citing is not warp drive and quantum gravity, but randomization and numerical linear algebra. This is a core statement about how our areas are progressing and so on.
Exactly, yeah. Yeah, so maybe one of the topics would be good to chat with you about, and it's definitely a hot topic at the moment, is the foundational models for science. I've seen quite different viewpoints. There's one argument that is, well, large language models take all this data from the internet, they train, and they're remarkably good at doing what they do. What about if we could do it for scientific disciplines? Wouldn't we be able to just, ask a prompt to go and simulate me a plane or do something? And then there's the other avenue, which seems to be more the replacing simulation tools or augmenting simulation tools like GraphCast or ForecastNet or, these sort of seminal pieces of work that have come out, but they were they had to be trained, for something. Where do you see this Where do you see this going? Are foundational models possible? Is it we just don't have enough data? This is a big topic, so I'm not sure how we want to start this.
I mean, we're in the middle of this fray, and I guess is why you're asking about this. And I should start off by saying I don't know what a foundation model is. Actually, I know what different people say a foundation model is, and it means very different things to different communities. And so I think articulating that a little bit helps articulate some of the possible directions and some of the questions you're asking. I mean, I think one way to think about a lot of these machine learning methods, and it's highlighted particularly cleanly with these foundation models, is machine learning methods, and in particular these foundation models, they're an infrastructure, right? The Stanford report said call it foundation models, not foundational models, because it's a foundation on which you build things, and as opposed to a half dozen other terms they could have used. Now, whether that's right or not, I mean, but that's what they said. And so since then, people have said, well, it has to be this big and that big and whatever. And then people want to get a foundation model, not for all of science, but for area A and B and C and sub-area D and E and F, and get finer and finer granularity. So in a sense, it's a term. And if you ask people, most people using it, what it means, they sort of will acknowledge that they don't know, and it's not a standard definition. I think probably the best way to think about it is it's infrastructure. It's a foundation on which you build things. And so the computer's infrastructure. I mean, you can do different things with a computer than you can do with pencil and paper. And so it wasn't obvious the way computer science, even before it existed, would evolve. And at one point, post-World War II, the U.S. thought they'd need 5 computers, and that would be it. And it would solve all the nation's needs, right? So it evolved in ways different than expected. And it evolved in particular because it could complement what people did. I mean, you could ask different scientific questions than you could with pencil and paper. And you could ask different engineering questions than you could. I mean, now you can simulate whole things, and the very, very last step is building it, right? But in addition, you could do lots of other things that were driven by industry. And so there's a bifurcation in the area, whether you're doing more numerical things that are continuous or whether you're doing discrete things that are not continuous, that were driven largely sort of by business needs. So I think the right way to think about this is it's that sort of infrastructure, and it's tied to the data more closely than database systems, because the foundation models have information cooked into them. And so it wasn't obvious some number of years ago that just with language you could do what has caught the popular attention in the last couple of years. So I think sort of anyone who says that confidently you can or you can't with science, I mean, probably you can't say that they're sort of reliably saying what will hold for the future, because I think it's not at all clear. I think it's not at all clear for 2 reasons. One, there's certain technical things that really do matter. I mean, that are different about scientific data than language and vision data. And then there's just very different cultural things. I think every scientist thinks that their data is special and unique, just like they think that they're special and unique. And if ML's taught you anything, these algorithms can predict what movie you'll watch and what stuff you'll buy better than you can. And so you're maybe slightly less unique, than you thought in some sense. And so I think there's a question, what does foundation model mean and how can it be used? So narrowly, I have a big model. I can train it in domain A. Domain A could be weather and climate have gotten attention, but it could be fluid dynamics. It could be something else about stellar formation. It could be properties of materials and doing density functional theory and so on. And then there's a question about whether you could maybe learn broad-based models that cut across domains, which would, of course, be the more interesting thing. So there's something, Kronos, that I was involved with the AWS people that sort of says, I don't want to be the best at the most extreme things. I don't want to be the 1% that's predicting the most extreme things. I want to do as well as the majority of users for time series analysis. And to oversimplify the story, I mean, time series is a complicated area, clearly of interest in a lot of cases, but it's a little bit, you got to be careful about off by 1 errors and a range of other technical things. And what that says basically is take a language model structure with a bunch of time series and just mean center it and variance normalize it. So just do the simplest possible things you could. And you got to do some data augmentation stuff, and boom, you do sort of comparably and better than a wide range of public benchmarks. Now, the public benchmarks are not extraordinarily high because a lot of time series data is valuable, and so companies tend not to release it. But the fact that you can do that just by sort of variance normalizing and mean centering is not obvious and sort of interesting. It turns out sort of on a separate thread that you could say, could I do well compared to the 1%, the most extreme things? And the answers that you can there too. You got to use different techniques than you do there. And so that leads to questions as to whether you could have a foundation model for sort of a broad swaths of time series and forecasting analysis. And so, as you know, I said I'm an Amazon scholar working with the Scott team, and we're looking at that there. And one of the interesting things I think about there, if you look at the details of the model, not the Chronos, but some other things, why would you expect that articles scraped from Wikipedia, publicly available language models, why would that allow you to do a better job predicting dog food demand? It's not obvious they have anything to do with anything. It turns out, I suspect the hypothesis is that the text, the linguistic structure you're learning from the Wikipedia articles is strongly related to the sequence-to-sequence modeling, which, if you think of one dimension as a metric space, it's a very, very special metric space, a very specially structured metric space. And so you can learn not just recent information and not just low-frequency information over the past, but maybe information at different scales, because sometimes articles in text refer back 10 words or 100 words or 1,000 words or 10,000 words. So you can learn these sort of heavy-tailed sort of structures. And that gives you a better set of basis functions to learn dog food demand or whatever else. So in a sense, the language models give you better embeddings, Fourier analysis and Laplace transforms and these sort of things are great for pencil and paper. They're all developed in the 1800s, right? These are data-driven embeddings that are good if you have computers and data, not necessarily for pencil and paper, but they're good for that. And so that leads you to the question about if I'm really careful about doing foundation model work in science, what do I need to worry about? It's not the details of this PDE or that PDE. It might be that I want to reproduce what happens in the natural language processing, the NLP models, which is roughly scale model and data and compute, so none of them saturate. And that's very different than the usual strong scaling and weak scaling and high performance computing. Right? I want to change the amount of data I'm putting in. I want to change the size of the model. I want to change the size of the compute so none of them saturate. And the conjecture would be that if any of them saturate, it's going to be harder to do transfer learning. So you really need the non-saturation. And you do that one way with NLP, natural language processing, and CV, computer vision. But in NLP and CV, there's much weaker control you have and that you need on the spatiotemporal geometry than in PDEs, right? As you know, PDEs, if you're below a Mach transition or some other physical transition, things are sort of smooth. If you're above it, things are very messy. Dealing with that transition is hard, and people spend their whole careers dealing with that. So can you come up with data generation or tokenization mechanisms that respect the spatiotemporal properties? So I think if you're going to have a foundation model that applies across a broad range of sciences, that's trained on weather and climate and simulations of different grid structure, from the machine learning perspective, it's not so different than satellite data from satellites looking down. It's a different grid and it's an image. And then you say, how does that couple with the spatiotemporal properties? So I think if you want to deliver on the promise in the same way as computer science had to work out a range of numerical methods to really match and beat state of the art, you're going to have to do a similar thing here. And so partly depends on these technical issues, but partly depends on cultural issues.
But how much do you think, you raised the 1% versus the 50%. I guess that is one argument as well, which is how close does it need to be to machine accuracy to be useful? You could argue that any of these large language models, the way that most people use them, there is still a correction you need to add. You don't typically ask it to do something, write a document, and literally take it word for word. You usually go in and go, that's remarkably close, but I'm still going to go and fix it. Or it writes you a Python code. It's unusual, isn't it, that it's perfect. There's usually some thing you have to correct. So I guess with the science side, maybe the argument is how close does it need to be useful, and the cost of getting the incremental increase in accuracy. Is there a trade-off where you need so much more data?
Yeah. I mean, again, I think the best analogy is look at the history of computer science and how that evolved. I think framing the question to say how close does it need to be useful, you're already framing it in a way that that makes one group comfortable, the numerical analysts and the PD people that frame a question a certain way. That's not how people would have framed the question before. I mean, before you had represented continuous numbers on a computer discretely. Take a step back and say, I want to solve a certain problem. And the question is, now that I have very different trade-off in terms of compute versus data, and I have this new infrastructure that's language models, can I ask a different question and push the science forward? I mean, so for example, in chemistry historically, but also in nuclear physics and in fluid mechanics, there's this notion of a semi-empirical theory, which is a theory sort of derived, it's not just curve fitting, it's derived from an underlying more fundamental theory, maybe phenomenologically, with parameters that are then fit empirically or semi-empirically. And so what you need there is not the theory to be right, but sort of right enough at the level of, in the chemistry, is chemical accuracy, which is however many kilovolts or whatever. It depends on the reaction you're interested in and so on. And so certain methods that maybe were more principled were a bit too coarse for that, and other methods, when you combined it with other techniques, achieved chemical accuracy. And so none of them were low enough in the stack that they were better QR codes for QR from linear algebra, but they solved the downstream problem at that level of accuracy. Probably what you'd see here is that, right? So it's probably not going to be so successful to say I want to get 10 to the minus 16 or 10 to the minus 2 with my large language model. But a foundation model for science need not be an LLM. You could be literally learning the embeddings from a range of PDEs. You could train to PDEs of different types, and you could say, I want to port, if I know the basics of hyperbolic and parabolic, and I know that in the transport equation this can enter in a certain way, and you have nonlinearities and certain types of forcing functions, model each of those and solve each of the components separately. So I think the question is, what's the right level of abstraction to do that? And one of the modalities you could use is language, but of course you could use image or PDEs or simulations or any of a range of things. So I think in the context of scientific problems, the foundation model need not be an LLM based. I mean, there's some people who are pushing that, I think, but it certainly need not be LLM based, where you just query the model and say, tell me where to look for the top quark or whatever. But,
well, that's the bit maybe you brought up would be good, interesting to explore. There is I would say, a relatively fierce or contested argument around physics informed or physics in it versus data driven. Where do you sit on that argument? Does the model need to implicitly have some of the boundary conditions, some awareness of continuity of energy, or is it good enough just to give it so much data that it essentially learns those laws by itself?
Yeah, I mean, I think you could ask the same question about in natural language processing and computer vision. Did you just? I mean, there's a common story people tell, which is just get more data and everything works, but that ignores the fact, as you know, that a lot of companies and universities, a lot of people have put a lot of resources into NLP and CV to try and figure out how to make it work, and convolutions convolve things. They spread stuff out. If you have an image in 2D, that it may make sense that you might want to average over nearby things. But if there's a sharp corner, like the shirt against the background wall in this picture of me, you may smudge stuff out. And so there's a range of ways to try and sort of deal with that. That's core structure, the 2D structure that you're trying to average over, is very different than sequence-to-sequence learning. That's also much more discrete in natural language processing. So it's not like computer vision or natural language processing just learned stuff. You gave it very particular architectures that had very particular inductive biases, and then you were careful about the data and trying to get gobs of it, and then it worked. So I think if you'd have to follow the same path here. You can't just take an existing architecture and press a button and hope it works. I mean, time series forecasting, spatiotemporal modeling, these sorts of things will have to be, you have to figure that out, how to do that. So I think the question, I mean, some people, I think are, and maybe sometimes people that have a vested interest in moving forward or not. I mean, some people say, just ignore everything and let the data do it all. Some people say, oh, you'll never match what I can do with my careful PD solver. I mean, I think that's neither of those questions is the right one. I mean, the question is, given the fact that there's an infrastructure of code and experience numerically, but you're also at a very different place. You've been sitting on top of certain, essentially hardware and linear algebraic advances. I mean, for years, for decades, people working on PDs call certain linear algebra libraries and have essentially had not to pay the technical debt associated with the fairly high level of complexity with developing new linear algebra, almost because you just wait a year or two and the machines are faster. Yeah. And so if that's not the case, you're going to have to start thinking a little bit more carefully about the underlying linear algebraic computations. Maybe there's different trade-offs and points in the space, and maybe bring something else to bear. A model that has learned certain coarse type functions of one dimension, say from the language model that I alluded to before, that aren't Fourier modes or aren't Laplace modes or aren't something else like that they're more familiar with, learn a different grid type discretization. So I think the real challenge in delivering on the promise of all this stuff is figuring out what the right way to combine those two is. So you can imagine, rather than just writing down a physics-informed loss and pressing a button, saying, well, the way people actually would solve this is to have some sort of splitting method and deal with the two types of physical things and the diffusion and advection in two slightly different ways, and machine learn one and take the other as numerical, and then you couple them together, maybe in a differentiable end-to-end
Yeah,
way.
The reason I asked this is because it does feel, certainly at least in the CFD community, that there's a real sort of split within the community almost, and a sense that on one hand you have people saying, well, we have all these PDE solvers, developed for decades, and what convinced me how your machine learning or AI method is going to be as good and faster and cheaper, versus on the other hand you have quite sensational claims of 10,000 times faster, it's sort of real time. Well, of course, when you dig in, you start asking the questions, well, how much data did you have, what was the time to create the data? But there is a bigger question, I think, more when you look to the future, which is it just a matter of time? Is it a bit like in the 1980s they could only simulate a plane to a reasonably low accuracy because the computers just weren't power enough, and as you said, you just almost keep the same method, almost, and you just literally add 20 years of compute on top, and now you can simulate? Or is it we'll never get there because it's like it's like impossible to have that much data. Do you know what I mean? This is the bit I think a lot of VCs and startups are also asking that question. If we pump 100 million into this, or a billion, will we fix it? Or is it $1 trillion problem and it's not worth doing?
Yeah. I mean, okay, so I think there's a bunch of things in the question there.
Sorry.
Old school CFD people to VC, and that's because that they have two very different utility
motivation. Yeah.
I think, okay, so when someone says to me, do this, convince me of that, I have these metrics that I've worked on for decades, I just say, thank you, good to talk to you. I mean, because there's no way you're going to win that battle, because they're very fine-tuned metrics, so they're very one little use case. Even if you do win that battle, they're not going to admit it, because they'll tweak their method and be slightly better than you. And there's greener pastures for you everywhere. And this is not a hypothetical statement. This is a very practical statement. You're asking about this in the context of PDs. We saw this before in randomized linear algebra. I mean, so literally I remember it was very clear that the techniques could potentially be useful, not just in theory, but in practice. And that the reason the numerical people were saying, oh, they won't work, really, I mean, there was a number of methods that clearly wouldn't work, but then there was a next generation of methods, and that's sort of when I entered the area, and it was clear that they could potentially work, and the objections people had before wouldn't work. And so this was right around the time of the Blunden-Pick paper that I mentioned that basically said, can you beat LAPACK? And the short answer was yes. So now, for example, if you look at the SIME linear algebra meeting, half the talks are on this topic. But there's been this process of creative destruction where they're still asking the same questions, but putting randomness there. And so that's one group of community. I mean, a very different community is the people that say, I'm going to not do that. I'm going to go and apply it to machine learning and 10 other problems. And so there's that tension I was alluding to before. So I think if you try and satisfy an old school metric, it's good to have a few examples of that as proof of principle. Mm-hmm. And this is 15 years later, and I mentioned it twice here, right? I mean, so this was a clear proof of principle of the area. The area sort of accelerated after that, and there's been a lot of theory and empirical development. So I think there's been a few things that, if not that, are starting to look almost like that in this general scientific ML area. I think history's moving in that direction. So it's clear then that randomness would be important for linear algebra, and now it's even more so for all the historical and hardware trends we were talking about. I think likely the same thing's going to happen here, right? And so a question you could ask is, are the people who know the linear algebra, or the people who know the computational fluid dynamics, are they at the table developing the methods, or are they just going to poo-poo it and say, well, they're not going to work because it's not going to satisfy my particular measure? As opposed to, here's a broad class of techniques, and it's hard to imagine that there's nothing in my area that will be improved by them. And so I think that's that latter question is the question to ask. And that latter is the questions VCs and other people will ask. And I think an important maybe determinant of how this will evolve is how the different players interact with this, in the sense that a lot of the machine learning, more broadly, scientific machine learning, not just for the foundation models, more broadly, machine learning really is a horizontal. I mean, it's designed to say, what can I do with lots of data and be relatively ignorant about your application area? Because who knows why people click on ads or click on links on their social media account, right? I mean, you can tell the story, but really, who knows why? Mm. And so a lot of machine learners, implicitly or explicitly, will say, I'm not interested in solving your scientific problem if it's just a one-off problem. I mean, if you're a scientist using machine learning, you might be interested in that, but that's because you're interested in the domain. But if you're a machine learner, you might say, I mean, I see some commonalities between your fluid dynamics and this other solid mechanics problem. And I see some similarities there between that and something in 3Ds in the atmosphere, as opposed to something very different. And so identifying those commonalities, I think, is important. What I see in some cases, and this is hampered by universities, and it's hampered by industry, and this is hampered in a couple government labs in a couple different ways, is a lot of people want to solve a scientific problem, and so they're going to say, I'm only going to invest literally or figuratively in machine learning in that one area. And that's just not how machine learning works. You don't see think of it as business with horizontals and verticals. If machine learning is a horizontal, like high performance computing, that'll solve a wide range of problems, you got to apply it to a vertical to justify it. That's where that's where the rubber hits the road typically. And so you don't see the successes in machine learning, scientific machine learning, at vertical companies. Companies working in genetics or oil exploration or any of a range of other particular domain verticals. You see it in the horizontal companies, the companies that built out the technology infrastructure, and they get a team of people that know this is a vertical and applies it there. And then, a team that knows a different vertical and applies it there. Mm. And so I think the question is, how does that play out? And that's going to be a non-trivial evolution in terms of that day.
Your comment was interesting as well about the difference between sort of transformers versus CNNs. And, if you just throw the whole world's internet at a CNN, you needed to have the right architecture to be able to throw a lot of data at it. I guess the question is more for the science. Is there a common architecture across the sciences that then would allow you to sort of build out that big, which could be applied to verticals? Or is it the case that the needs for weather or genetics or chemistry are so different that you would need a different architecture for each different science, and therefore the dream of a true foundational thing for science, it will never happen because so
that's the big question. And I think there's a technical component to that and the non-technical component in terms of the areas, right? And so technically it's open-ended. I don't know, right? I mean, we're in the middle of the fray, and we're voting with our feet and placing a bet there that the answer is or could be yes. To try and address that, you're going to have to deal with the issues we were talking about before. One dimension is very, very special. 2 dimension, the surface area to volume properties are very different. 3 dimensions is very different. By the time you get 4 in scientific computing, that's sort of infinite, right? Machine learners, by the time until you get to 1 million, it still seems pretty small. So Mapping the methods to 1 versus 2 versus 3 dimensions, open question. Maybe there'll be no trade-off point where the surface area to volume and the isoperimetry and other things like that wins. I suspect not. I suspect it could, but I mean, open question. And then non-technically, if you look at how computer science evolved, numerical analysis and scientific computing was core to computer science. Look at how numerical analysis and computer science evolved. These areas gave birth to computer science, and then computer science banished them because it was easier to build the structure, the theory around Turing machines and the lambda calculus and discrete notions that talked about complexity independent of the data. And if you're talking about complexity independent of the data, you don't need preconditioners because it's independent of the data. And so there's a cultural aspect that says, does the vertical or the horizontal culture win here? And so even if you stipulate that the answer is technically yes, I think there's an open question on how it'll evolve and whether that'll win the day and solve the problems that you're asking. But I think it's not so much that I solved PDE type A and applied it to PDE type B. It would be certain coarse things. I mean, as you know, there's a class of things for which finite element methods work. There's a different class of things for which finite volume methods work. And you take a course, you learn a 101 method, and then boom, they bifurcate after that. So what's the analogous taxonomy here? And it's probably neither of those. It's probably something that's more data driven. But what's the right way to taxonomize that? And even if there's technically a correct way, I mean, computer science is not computational science. Computer science is an area with a coherent. Computational science is spread over many departments and many divisions. And so I think it's an open question about how this area evolves.
Yeah, it is certainly interesting. I think one of the sort of key topics to all of this, though, is the data availability and licensing and financial reward. So one thing that I've seen in, I guess, the early days is nobody knew what was going on. So I guess the companies were scraping half the internet. There were a few captures or there was a few sort of, firewalls to stop things. But in general, it was a sort of free-for-all, it seemed. Whereas now people have, cottoned on to that, and some of the companies are having to do deals with publishing companies or do deals with, to try and legally get access or permissively get access to things. I saw the example on the weather side that, some of those databases were released openly, and because they were released openly, it enabled, these various teams to go and do things like, ForecastNet and GraphCast. But those data may not be open in the future. So how much, and you work in academia, you see people want to have their own data, some people want to release it. Do you see that will ultimately be the blocker? I mean, how do you incentivize people to want to make their data available? And should it even be done that way? The whole open source data versus closed.
Yeah. This I think is the elephant in the room in terms of this area, because a lot of government grants require that you make the data publicly available in some sense of the word. Now, what does in some sense of the word mean? For a lot of scientists, if the data is more than a year or two old, it's worthless because they're trying to push the cutting edge of the science. And then they don't maintain the data for more than a couple of years ago, and so no one maintains and it's hard to access. So there's a lot of public data that's not de facto public or accessible. In those cases, and maybe but certainly in machine learning sort of applications more generally in internet and social media and so on. Having older data is good, but you can't get more than a couple decades older, right? And so oftentimes the most recent data is the most valuable, and you just design a method around that. And so it's not obvious to me that the way the data are generated and collected and distributed now will be the one that is developed going forward. I mean, if you get better telescopes, if you get better, molecular sort of robotic systems to make molecules, I can easily imagine a situation where data that exists now or prior to a few years ago is basically obsolete and irrelevant. And so all of that data sits at whoever generated it. And so then the question is does a government lab generate it? And if so, do they make it easy de facto to access? Is it done at universities where you have a big infrastructure capital investment in particular, essentially in particular science verticals to generate it? Is it done at companies that are in different verticals? or is there some sort of collaboration or interaction with horizontal infrastructure companies, hyperscalers, and then they get their fingers in that and have access to it. So I think these are all open questions in terms of how this evolves.
Yeah, it seems to be very much, traditionally, and I guess if this is, for me, the difference between the pre-trained, quote-unquote, foundational models versus just letting someone go and train their model. I mean, I guess most people, you and I, would not go and train our own LLM. We're just going to go and use someone who's already, and we're just doing an inference on it. And I could see if I'm BMW and I have data from previous car designs or simulations or whatever, how they could train a model using their data. But I'm sort of wondering in my head, how could it ever become the point where some person has access to not only BMW's data, but Fords and Audis and Volvos and Boeings and Airbuses and, ExxonMobil and Shell and everyone else. Like, how could they collect the data? What would be the incentive for that to happen? Or that's what I mean. Or is it the case that that's why there will never be a foundation, and it will just be that individual people train their own models because the data is just so sensitive and difficult to collect in one?
Yeah, I mean, I think this is the big elephant in the room. I mean, it's not clear to me that so I think if you were to try and generate a meaningful scientific foundation model, you'd need data from a pretty broad range of use cases. And so you gave several that in particular are where there's a strong sort of financial backing. I'm always reminded of the story. Gray was, I guess, the most prominent person in the Microsoft's research division years ago, such that he would have to have regular meetings with Bill Gates, the CEO at the time, and Bill Gates would say, "Why is the most prominent person in my research division applying databases techniques to astronomy?" This was when he started working with Alex Saleh and some others on databases for astronomy and cosmology. Why don't you work on something more useful, like any of our products? And Gray's answer was basically, "I'm working on it because it's worthless, because there's no financial sort of incentive behind it. I don't have to talk to the lawyers, and we can work out IP and all these things. It's public data, and I can work on database techniques and figure out latency and bandwidth and all these trade-offs." So I don't know, but it'd be interesting to see, will you have an analogous thing here? So there's various places where public data is available, and I think if you can illustrate that you would have a proof of principle foundation-like model, then the question is, will people come to it? Now, clearly the incentives for scientists will be different than for companies there. But I could imagine a situation where you build that out, and then companies could take it and fine-tune to their particular data, right? It's not obvious to me that any of the companies that you mentioned have data that is that special in a scientific sense. I mean, clearly the particular data they have is particular to their particular situation and then the particular product they have. But I can imagine that the PDEs from early solar system formation and hydrogen bomb explosions and hydrodynamics inside stars, has some similarities and some differences with weather and climate, and some similarities and some differences with crack propagation in the Earth. Mm. And that'll have some similarities and differences with various sorts of sensing modalities that have a geospatial component. And so can you stress test that and get even a proof of principle that if you were to tack those on, then the answer would be yes, that you could have a path to have a more foundation model. If the answer is yes, then the question is you talk to various stakeholders, some of whom are government entities or government sponsors, some of whom are corporate, and try and figure that out. I could imagine that basically it's too big a lift in the area of stalls. So I think this is something to be determined. But I think having a nucleus of something is going to be important, because right now, at least what I've seen, I mean, in most of companies like that, there may be some people a little bit intrigued, but there's not a sufficiently heavy lift that they go screaming at their CEO to say, we need to do this. Partly because there's not extremely strong baselines that it can happen, and their competitors, by talking to these public models and fine-tuning on their proprietary data, will do better. I think at that point, you could see a change.
And I think this is, I guess this is affecting the current Gen AI and AI, which is how do you make money out of this? Like you can do it for the sake of science. That's nice. Develop this thing, but I'm always interested to see like the money that you put in to create the data, to train the model. Can you ultimately make a profitable thing out of it that justifies its cost? Now, with standard, I guess, simulation software, there's an argument, well, if I simulate it, I don't have to build it. If I can predict the weather, I can help people figure out if there's going to be a hurricane, and I can say, there's a clear thing. But because we can already simulate things, we can already predict the weather, we can always do it. For me, the machine learning bit is just the argument, well, it's faster or it's cheaper. That's where the amount of data. Do you know what I mean? Is there a commercial?
Yeah, but I think there's a faster question, and I think it's tempting to say, can I be faster? Because faster means there's a number you're comparing to. So am I bigger? Am I more on some axis? And back to the randomized linear algebra example. I mean, I was talking to various people and saying, don't worry about the randomness. If you do this and that, it'll work. And the people would, basically, when you have a new idea, they'll beat you up. And so they beat us up and so on. And a few years later, one of those people in particular had some methods and showed it worked, not the blended fit, but something around the same time. And their students came back to me and didn't know who I was and was lecturing me and saying, oh, don't worry about the randomness, it'll all be fine and so on. There's just a cultural shift. And so there was a cultural shift that really was not, is this faster, is this better? And so I don't think you're going to see the win here just because something's faster and better. You might need that to point to. But the win will happen because you can solve other things that you couldn't solve before. So just as an example, say you want a better battery and you want to understand the way crack propagates better, so that you want longer lifetime, warranties. So you're working on developing batteries. One of the ways this fits in, not in a scientific but in an engineering or commercial context, is you want to write a warranty to say that that the batteries are going to last so and so long, and otherwise you'll eat the cost. And so can you predict battery lifetimes? And maybe if you have a certain crack propagation heterogeneity structure, you know that it correlates better with how long the batteries will last. Because now there's a fair variability, and in particular on the extreme tails. So that sounds sort of very different than I want to do oil exploration and better fracking or something. I send sound waves down into the earth and I look at how they bounce back and I try and learn something about it. But I could imagine that the embeddings that you get from a core model that cuts across a couple different domains learn spatiotemporal properties, in particular of complex systems that have sort of long-ranged, non-trivial, heavy-tailed correlations, which is what both of those examples have. And so say that you can come up with a model that captures those embeddings. Now a company here may tweak it to their data, do some transfer learning in the battery space. A company over here could do a better job adjusting it to their data, which is spatiotemporally very different in terms of better fracking. And for all I know, the same embeddings could be useful for yet a very different use case, right? And certainly in the United States, there's various places where insurance markets don't exist for floods or for earthquakes or for a range of things like that. I could imagine that you get these coarse embeddings. These are coarse functions. They're not sinusoids and Fourier modes. They're something that's data-driven embeddings. And you say, on top of that, I want to do transfer learning to the relatively small amount of data that I have that's very high touch. You have 10,000 stations across the country that measure something, chemicals or whatever. I want to do transfer learning to that, and I model the system the way information flows in the Mississippi Delta or something. And if I do that, I can do a better job, predicting the tails of flood events. Why? Because as a model, I know how things propagate, but subtle effects in terms of the density of the soil or the moisture of the soil, coupled with 10,000 other things that the neural network learns in a complicated way, but it's hard to reason about scientifically, means that now I can create that market. And that's something that any of those companies I could imagine try and buy out a startup company that does that. So I think you're going to see a win, not just I'm running faster, something faster than you, but in a space like that.
Yeah, no, I think what you're getting at is what we've seen from current machine learning. It seems to do things that we don't fully understand, but are like you gave the original example of the time series, that an LLM that wasn't explicitly trained on it actually ended up being quite useful. So I guess we shouldn't underestimate the potential of how some of these things may do something that it's not just about replicating what an existing simulation tool could do, but maybe it could help to merge different disciplines together and see the links and the things between it. I did want to pivot to a different topic, which is when some of the other people I've spoken to, I'm always really fascinated by the curiosity or the uniqueness or the peculiarity of academia, and sort of different people's careers and progression through it. And I think you have quite an interesting one because you are a very pure mathematician, academic. You are very much in that, but you also have, the Amazon Scholar position. You at the, Lawrence Berkeley. Was this a strategic thing in the sense that you wanted to work on real problems? Was this just you find more interesting? Is there how has it benefited you, and would you advise it to others? Yeah.
Yeah, I mean, there's a lot of questions. I mean, at least the narrow question is universities versus not.
Yeah, there you go. Let's start there.
but you tapped enough stuff into the question to make it forward compatible with lots of answers. It sounds like. I mean, so my PhD was in physics. I never actually studied computer science or statistics, and it was in computational statistical mechanics. And at the end of the dissertation, I switched areas basically to theoretical computer science to work on originally Markov chain algorithms. Some of the stuff I had been working on computationally were Markov chains and molecular dynamics, so it was a technical connection, but it was fairly loose. And then the randomization inside the Markov chains, the people I was working with were also working on these very early versions of these randomized linear algebra algorithms. So I got involved with that, and I'd done enough coding that was clear certain ones were going to be useful and certain ones weren't. And so at that point I decided to switch areas, partly because what I had been working on, two reasons. There was a forcing function. I just mentioned this because if you have younger people listening, it's good to know that sometimes older people have had a textured past, let's say. So long story short, I had career-ending problems with the dissertation advisor, and the supply-demand structure in the natural sciences and engineering is very different than in computer science. And so that was a motivation to jump off the cliff. And I also realized that the particular work I've been doing in computational statistical mechanics, this is a great area. I loved it, and it's informed a lot of the stuff that I've done since then. But it was a great area to be in 1970 because forward compatible with huge expansion. There's going to be Nobel Prizes given out. I mean, just lots of good stuff going around. Not so much in 2000. The area had sort of saturated, but it was clear that that the future was going to be data analysis. And I joke that I never knew more about algorithms or data than the day I switched, and then I've just been becoming more ignorant since then. So I don't know quite what I meant by data analysis then, but clearly I was right. I mean, it was a fruitful area for the next couple decades. So I'd done work in theory of algorithms, and with respect to the academic question, if you're desperately wed to an academic career, you shouldn't do this because the academic hiring is fairly siloed, and it's not a good idea to switch areas after your dissertation and so on. If there's a forcing function like I had, or you're interested in sort of problems more broadly, then you can think a little bit more broadly. So I've had a lot of students and postdocs, and I sort of give them this advice, and you try and carve out various projects that they're interested in. Some want an academic route, so they should work on slightly more conservative things in the general space. Some definitely want industry, and some could go with either. And the ones that could go with either, I've seen some go one way and some go the other. As a general rule, this is going to be a marketable space, the stuff I do, and so maybe it's a little bit less of an issue. But that's something that they figure out. So I had done work in theoretical computer science, and it was clear that these algorithms would be useful more broadly because the randomness entered in a very different way than classical algorithms. And so then the question is, how does it evolve? And so it evolved. I was at Yale in the mathematics department as one of the junior faculty positions. I spent time at Yahoo and Stanford and moved to Berkeley. I'm in the statistics department there. and at the International Computer Science Institute and Lawrence Berkeley National Lab. And as you mentioned, a couple of years ago, started with as an Amazon scholar working in the supply chain optimization technology group, where we work on better forecasting, demand forecasting algorithms and supply chain decisions. So I think this is something that's good for people to think about. And there's at least, I guess, 4 hats there, and each hat has pros and cons and pluses and minuses. And so figuring out how to navigate that space is something I try and encourage students and postdocs to think about sooner rather than later.
How much should people expect to have to move? I always think this is one of the sad, in a way, things about academia, at least from what I've observed, the fact that you do your PhD, and let's say you do a postdoc. How realistic is it that that person in the US or the UK should assume that they can stay at that same university and just move up the chain? Or how much should they expect that they're basically going to have to move somewhere else in the country to find the position?
Yeah, I mean, the short answer is that when you do a postdoc, it's usually more targeted because you're working with a particular person, a particular group, and so you could be at the same place or not. It's usually a good idea to go elsewhere to get experience with other people. The real filter's at the assistant professor level, and you got to move there because, except in rare cases, you don't get a job at the same place. And that's not a statement about whether the place where you are at is good or bad, or whether you're good or bad. It's just run the numbers, right? If there's 10, 20, 30, 40 places hiring that you're looking at, and the chances are 1 in whatever that you get an offer, it's just unlikely to happen at that same place. Even if ultimately you end up there, sometimes people go and leave and come back. So moving, for better or for worse, is part of the equation. Yeah.
But some of the questions I get is should they go into industry, or just, let's put this 2 ways. Does academia value industry? So if you've been an assistant professor or you've been a postdoc and you then say, I'm going to go into industry, do they value then, and is there ability to come back? Or have you been out of the game too long? You haven't sort of, got the publications or the teaching experience, is that a good piece of advice? Or would you say, no, if you really want to be in academia, you basically need to stay in academia?
Yeah, I mean, it's more texture than the following, but I think the short answer is that you need to stay. The slightly longer answer is it depends on the area. Like computer science versus statistics versus engineering are rather different. In some cases, having a startup, in some cases, having a postdoc at industry is good, and you can go back to universities, and that tends to correlate with computer science. I don't know as much in engineering. That may be changing over time, but less so in maybe statistics and applied math. I think, in a sense, on the one hand, people value the experience you might have, but not really. And by that I mean, if you check all my boxes, and in addition you have this other stuff, good. But you got to check all my boxes, and the boxes are the things you alluded to. And so there's sometimes postdocs at industry that are basically academic postdocs. You write papers. So I'm not counting that because that's de facto the same sort of thing. But if you're out more than a couple of years and you have fewer papers, it just gets harder to publish. There are certainly cases where people do that, especially if they have some high-profile ones and can work their way back one way or the other. But it's, you should know going in that it's like a salmon swimming upstream, and it's just going to be a hard battle.
So how does he, this is maybe people in the US are maybe a little bit more familiar, but particularly people who are not. So how does it work with the national labs? So you have a position at the national labs. How does that work between, is this a quite a common thing in a way for these things to happen? I can only imagine how you juggle the email inboxes and the sort of meetings. But I guess it's valuable and interesting. I managed to
block off an hour today, and I haven't been hit by email. But that's because I've turned it off. But that's the exception. Email is a little overwhelming. I mean, it's not so common. So I with the Berkeley hat, because I'm in the statistics department there, I'm at Lawrence Berkeley Lab. It's literally just up the hill. and so you can walk there. And so they were interested in scientific machine learning, and I had done work and was well known in machine learning and algorithms and statistics, large scale statistics. And I had various projects over the years with people there and elsewhere on scientific ML problems. And so started about 2 years ago, we renamed, but the scientific machine learning group, basically, MLA, machine learning and analytics. And so was partly facilitated for the fact that there is a moderate amount of interaction between UC Berkeley campus and LBNL, Lawrence Berkeley National Lab. Oak Ridge, Argonne, some of the other labs have things like that, but it's not so common. Most people are there, meaning just there, and 100% of their FTEs there and there for long term. But so it's not, I wouldn't say it's very common.
Okay. Which makes your experience even more unique then to have done it. Well, maybe as a sort of finishing off comment or topic is, if you had somebody now who was wanting to get into scientific machine learning, because this is, I guess, kind of what we've been largely talking about, what would you get them to focus on? They're doing a PhD or they're doing a postdoc. But is there any? It doesn't have to be a very specific. But what sort of area would say this is something you should look at? This is an area that is ripe for progress.
Yeah, that's a good question. There's certain things. I mean, that are less ripe for progress in scientific ML, even if they're important scientific problems. So what I would try and say is you should work on a problem that's of interest to both sides. Otherwise, you're coming at it from one side or another. And this is true whether you're coming from CS or stats, learning scientific problems, or coming from one scientific area. You should work on try and figure out how to frame what you're doing as something of interest to both sides. So when I have projects that we construct projects, a student or postdoc owns a piece of it, and a goal typically is we want a publication in the particular scientific area, but also in an ML venue. And it needn't be the same one. Sometimes it's a long version, a short version, sometimes it's just two different things. But work on a method that's broad enough that machine learning people are interested in it, and that by the definition of machine learning people are interested in it, you convince 3 reviewers to say yes. And so it's an imperfect process, the review process, etc. But boom, you get it in a top machine learning venue. And similarly on the scientific side, a statement that it's a value of the scientist is you get 3 reviewers to say accept, and it's accepted on the scientific side. And oftentimes the way we try and scope out projects is to say, we don't, on the machine learning side, we don't want to work on your problem if it's only of interest to you, if I can't apply it to some other area, someone else, some other domain. Because if that's the case, I probably need to know so much about your area that I become, an expert in your particular area. And similarly on the scientific side, if you have a particular method that's so heavily tailored to your domain that it's not going to be useful more broadly to machine learning people, that's a much harder sell. Then you're not doing something that satisfies both sides. So something that I knew about from working on years ago is like sequence alignment in genetics, right? Clearly an important problem, not something that's portable, the particular algorithm, not something that's portable to lots of other scientific areas, but better machine learning methods for solving spatiotemporal forecasting problems with non-trivial boundary constraints. That's clearly of interest to a pretty wide range of applications. And also, to solve it, you're going to have to introduce technical solutions that are probably, can you come up with a differential optimizer for an end-to-end differentiable system where you have hard constraints? I mean, that's clearly something of interest to machine learning and optimization. So I guess I'd try and focus on something there, and that is probably the way that you're going to be, and unless you know exactly what you want to be doing 30 years from now, that's probably the way to make yourself most forward compatible with however.
That's a really good point. I guess what you're saying is, yeah, it's true. Like later on in your career, you become established in a certain area, but most people during their PhD or the postdoc at that time have no real necessary idea. So you're saying if you do something broad enough that can get you exposed to different groups and have a foundation, to your earlier comment, you can more easily go into verticals because you've built that foundation. Whereas I guess if you jump directly into a vertical right from the beginning, for you to sort of reverse out of that, it's kind of harder, isn't it? So I think that's what you're alluding to. It sets you up better.
Yeah. Because it's not at all, I mean, all the questions you're asking are fair ones, and it's not at all clear how the whole area will evolve. And so depending on how it evolves, having experience in one versus another, and I think, I mean, having worked in a bunch of areas, you know, it's but speaking substantially only English, but a little bit of other things, I can imagine, and I see, you know, you learn a second language, it's hard. You learn a third language, the relative cost is a lot less. You learn a fourth, I mean, so there's a diminishing returns in terms of the amount of extra effort you need to do. So you work in one area, you switch to the second, it's very hard. Switch to the third, you know, you can do that. And after that, one thing I've sort of been always struck by is it's amazing how little you need to know about a particular area, especially if you're working with good people who'll complement what you're doing. You can learn from them, right? And so it's amazing what you don't need to know in order to get interesting results in an area. And so being learning new things, by the time you know two or three things, it's easy to learn the fourth.
No, that makes sense. Well, thank you so much. I realize it's the day after Labor Day, which means that probably there's a whole bunch of emails and stuff that's starting to come through on essentially your first day back. And I know we probably could have carried on for another couple of hours, but thank you. Really appreciate it, and look forward to catching up in person at some conference in the future.
Sounds great. Thanks for having me. This has been fun.
All right. Cheers.